next session is going to be on the topic data, Firehose, and how to stop worrying about it. And we have the next speaker, Mr. Harikrishna R, who is on the stage already, co-founder and director of Klar Systems. Ladies and gentlemen, Harikrishna R is a co-founder of Klar Systems, where he designs and builds cool new gadgets. So that's really amazing. Applications and platform for Klar era. Prior to Klar Systems, Harikrishna was with Texas Instruments for over 15 years, where he helped designing digital signal processes for multimedia applications. So this is going to be a very interesting session for all of us. So ladies and gentlemen, let's put your hands together for Mr. Harikrishna R.
All right, this should have worked better, but it's not. But are you able to hear me anyhow? Not really? Can you check the mic? Is my mic working? Hello. AV issues. Hello. Any better? Okay. I'll put it back in my pocket. All right. So, how many of you here think IoT is overhyped? Quick show of hands. Nobody. Everybody thinks it's fine. Wow. Okay, how many of you think my topic for today is a little over the top? Urmi, can you help me? Can you put up your... Okay, so can you do me a favor and put up your phone? It's not working as intended. I had... it was working reasonably well before, so what it's doing here is counting the number of phones that have been put up. There it is. And showing you that count. It gets a little bit smarter, so I developed this demo exclusively for this talk. It gets a little smarter. Sometimes it finds patches of gray that it thinks is a phone mistakenly, this gentleman's head for instance, and then later it recognized that it's part of the background. And I thought it would be cool to show a demo, to begin with a demo. Anyhow, so much for that. My name is Harikrishna. I'm an embedded systems engineer, have been for a very long time. Most of my life I have spent designing audio systems for infotainment, audio compression, audio processing, that sort of thing. I've done a little bit of video, but mostly that. About 2 years back, I set off with a couple of my friends, my good friend Urmil here, as well as another guy, Mohan, to build cool IoT products. You know, boxes with blinking lights. It gets me excited. And I'm also partnering with Jigsaw Academy to develop a course on IoT. So that's a little bit of my background. And to me, as you can see, a lot of my life is around IoT, and I sometimes worry, is this getting a little too overhyped? Are we going overboard with our expectations for this new technology? Is it all going to just end in another crash, right? And whenever I think that, I remind myself about the foundations of IoT. When you think about IoT, there are basically three technological drivers underpinning IoT. The first of these, and the most famous, is of course Moore's law. Moore's law, formulated back in 1970s, basically says the number of transistors on a silicon chip is going to double roughly every 18 months. It was a bold prediction when it was made, and it looks extremely bold now, and yet it has more or less held true for the last 40 years. It's incredible, right? And there is no shortage of people coming and saying we are at the end of Moore's law. Moore himself, in fact, made that prediction, I think, during the 90s. He said, we're coming to the end of the Moore's law, and every time it happens, people figure out some other way to make transistors even smaller on silicon chips and to keep the law going. Now, when you think about Moore's law, you're probably thinking about Intel AMD chips that power your laptop or server class devices. But Moore's law is applicable to all semiconductors. It affects all semiconductors. Now, when a new technology debuts, right, like 14 nanometer or whatever, it's first going to be used in high-end chips because that's where the money is, right? But eventually, it's going to come to all chips, that technology, right? So if you look at this graph, it has a lot of predictive power. In 2004, you could have looked at this and said, smartphones are going to happen. Now, at that point in time, you have no idea what people will do with smartphones, right? But you know that devices that sit in your pocket and can do, with all that computational graphics power, that was inevitable at that point in time. And today, Moore's law is beginning to impact another class of chips that are everywhere. And those are microcontrollers. Microcontrollers are in pretty much everything. They're very silent workhorses of consumer electronics. Think about any gadget in your house, your washing machine, your fridge, your air conditioner. They all have at least one microcontroller in them, sometimes more than one, right? Even things like toys have microcontrollers in them, right? And for a long time, microcontrollers were a quiet part of the semiconductor market. They were like 2 to 4 megahertz, 8-bit devices. And they have mostly been going down in price, right? They've gone down so much in price that now microcontroller manufacturers are looking at adding features rather than just reducing the price, right? So today's microcontrollers are now running at 150 megahertz, right? And when they earlier had like 256 bytes to work with, today's microcontrollers often have 128 kilobytes or 256 kilobytes. They have megabytes of flash memory. That may not sound like much, but in the microcontroller world, that brings up very exciting possibilities, right? That means any one of these devices can get smarter with almost no additional costs. The second big driver for IoT is connectivity, ubiquitous connectivity, broadband internet, mobile connectivity. And that stuff is being augmented by a bunch of other connectivity options like NFC, LoRa, which is for low bandwidth, high range communication, and so forth. So it's easier than ever before to connect a device to the internet. That's the second driver. And that is also something that, when you think about it, is more or less inevitable. I mean, mobile connectivity costs, broadband costs are going down. It's going to be easy, cheap, and effective to connect all of the devices to the internet. Again, you don't know what you're going to do with that connectivity, but you can tell that it's going to happen. And the third trend driving IoT is sensors. This is maybe a little bit less noticed, but it's actually very, very, very important. Vincent Cerf, the father of the internet, he said the Internet of Things is really the Internet of sensors, right? What sensors do is take human beings out of the equation when it comes to IoT devices. The device is no longer dependent primarily on human input to function. It can sense its environments and it can influence it, right? There are some sub-trends that are driving, what has changed about sensors in the last few years. The first is digitization. Pretty much anything that you may want to sense or measure, temperature, pressure, but also things like location, things like acceleration, all of that has been digitized. And the second is miniaturization and modularization. even when you had digital sensors, when they first debuted, you had to have custom analog circuitry to make sense of the data coming out of the sensors. Today, you get like pre-built modules, often everything integrated into a single chip that allows you to just focus on getting the reading rather than in tuning or calibrating your sensor. And this is helped in large part by things like MEMS technology. MEMS stands for micro electromechanical systems. So the accelerometers, the gyroscopes in your phone, these are built using MEMS technologies. What this allows you to do is essentially build small moving parts on a silicon wafer, right? It's incredible when you think about it, and that allows all manner of miniaturization, all manner of reduction in costs, and it's really opening up a whole new bunch of sensors. So the trends underpinning IoT are kind of solid, right? We know these things are going to happen, and we know that the number of devices connected to the internet are going to increase. And the predictions are all over the place, right? From 50 billion to 26 billion. And it sounds a little incredible until you realize that we are already at like 15 billion connected devices today in 2016, right? So the big question really is, what is all this technology going to be used for, right? And if you read about this, most people, what they're doing is they're looking at some big problem or the other, and they're saying, okay, how can IoT solve that problem, right? And they come up with some imaginative solutions for everyday problem, and I think this is a valid approach. But on the other hand, it does not have a lot of predictive potential, right? These are exercises in imagination. The way a society embraces a new technology is an extremely nonlinear process. It depends on what some particular company does at some particular point. It depends on hundreds of other social factors. Even established technologies, if you think about the internet, it gets used in very different ways in very different parts of the world, right? And IoT as a technology is even more diverse, and we really can't tell how these things are going to be used. Instead, what I like to do is look at the technological possibilities from the bottom up, right? I look at change as it is happening. I look at possibilities that are opening up as new devices hit the market, as new technologies hit the market, and new connectivity options hit the market. I like to understand what the trade-off is with each new technology and add it to my toolkit, right? Now, having these technologies in your toolkit means that when you do encounter a problem, you have a large choice in terms of what you bring to bear on that problem, right? And so for today's workshop, I thought, why not do this counter? Now, it doesn't work very well, but what the hell? It did work at some point, and it can work. And what I wanted to do is just talk about it so you understand what the trade-offs are, or how it was put together, and why it suddenly became possible. Right? So what is happening in the demo is that I'm getting input from a camera, a standard issue webcam, and then I'm processing it and somehow producing a count, right? So what did I have to do with it, right? Now, if you've never done video analytics before, you're probably thinking this is a complex problem, right? But it's not. I had like 6 steps in there, all fairly simple. Actually, even the contrast step is not being used. About 5 steps is all it took, right? Let's start at the beginning, the image. The image, as I said, comes from a standard web camera. It's a pretty decent web camera. It's an HD cam, right? And an HD cam gives me 720p video. That means it has 1280 columns and 720 rows, right? That's a lot of data. That's nearly 1 million pixels. That's why it's called a megapixel camera, right? And each of those pixels is a 24-bit number with RG and B planes, right? Now, when you do the math, each image comes to 2.6 MB, and once you multiply it by the frame rate of HD video, which is like 30 frames a second, you're looking at a humongous amount of data. You're looking at 600 Mbps, right? And yet we stream HD video all the time, right? That's made possible by compression. H.264, for instance, can take HD video and easily compress it down by a factor of 200, right? Especially if you have low motion video. You can bring this down to 2 to 4 Mbps. That's the kind of compression technologies that are available today. But this talk is not about compression technologies. I mean, we need to deal with this video. We need to go through every one of these pixels to find out whatever it is you're looking for. In this case, I wanted to look for black patches, people holding up their phones. Right? So I have a lot of work to do. Let's say I take this image and spend just 100 cycles processing each pixel. Right? Once again, when you do the math, that produces a very big number. 2.7 gigahertz, right, of processing power I need to just spend 100 cycles on each pixel of my HD image. Now, about 5-6 years back, even this number would have looked pretty daunting, right? But today it's within the reach. But actually you can do better. You can just drop the frame rate. If you drop it to say 3 frames per second, that sinks by a factor of 10 to 270 megahertz, right? And all that means is that instead of processing 30 frames every second, I'm processing 1 frame every 333 milliseconds. That still is pretty good for generating good quality data, right? Especially if I'm doing video analytics. And actually in the demo that I showed, it was running at around 10 frames per second. So let's go back to the steps that I'm using. The first step, of course, is to take the image and convert it to a grayscale image. I'm only interested in black or white. So you take the color image and convert it to grayscale, right? It's a simple arithmetic operation. It's a weighted sum of RG and B pixels. And once I have the grayscale image, I want to do a thresholding operation. I want to find the black regions and leave out the white regions, right? Now the problem is, if you just blindly apply a threshold, you get a lot of problems. You get a lot of streaking. There's a lot of noise in the pixels that you're getting, and that kind of will show up on your image. So what we do is a little bit more clever. We do something called hysteresis thresholding. Hysteresis refers to any process in which the output is lagging the input, right? So what happens in hysteresis thresholding is there are 2 thresholds, a high and low. And if a pixel is below the low threshold, you decide that it's a black pixel for sure. If it's above a high threshold, you decide that it's a white pixel for sure, but you're not interested in it. All the pixels that lie between are the interesting ones. And the algorithm says, if the pixel between the threshold neighbors a black pixel, then turn it into a black. Now, if you think about this, this is a recursive process, right? What happens here is, you start with an image. Hang on a second. You start with an image, you do your first pass of thresholding, you get black, white, and gray pixels. And then you start growing the black pixels to encompass all the gray regions in multiple passes until you get to a point that there are no more black pixels to find. And at that point, you can eliminate all the gray pixels and get your regions, right? And once you have your regions, you're dealing with much less data, right? You start with an HD image, and you're left with, say, 5, 6, or maybe 10 blobs of interest, right? And then you can apply heuristics to those blobs of interest. You can eliminate regions based on their size. I mean, you expect the phones to fall within a particular size range. So the big ones and the small ones can be eliminated. You can eliminate them based on aspect ratio, because phones will fall within a certain aspect ratio. And then you can look at the long-term persistence of certain regions and decide that they are part of the background. For instance, the speaker over there, or even dark regions in the room can be eliminated, right? And that's it. That's about it. You do this, and you're able to generate data out of just a plain camera image. So at this point, you're probably thinking, so what is the point of this, right? Well, the point I'm trying to get across is, it is today easier than ever before to sense the environment and extract data from it, right? Far easier than you think. Now, what you do with that data, that becomes a more interesting question. I used, for instance, a simple algorithm that looked for black regions, and that was fairly simple to do. But the moment I want to do something like gesture recognition, right, it becomes a lot harder problem. I need to get into machine learning, and the problem with doing machine learning on images is that the feature extraction itself becomes a project in itself, right? I mean, where do you start? You can't just take the entire HD image and try to train your algorithm on top of it. You first need to do some pre-processing, extract some features, and then build your network on top of it, right? And those things tend to be a huge project, and they tend to be very, very dependent on the environment in which that sensor is